Recording started.
Okay, I want to welcome all of you back from the weekend, and of course, you're welcome to another session of organic chemistry lecture. In today's session, of course, we are going to finish chapter 17 that we started last Thursday. But before we do that, just one announcement to make. Tomorrow, that is Wednesday, at 7 p.m., that's Wednesday, February 8th at 7 p.m., there will be an online session. For that online session, we are going to use the end of chapter questions in chapter 17 of our. Okay, so the session is tomorrow, that is Wednesday, February 8th at 7 p.m. I will send you a reminder tomorrow, just in case you might forget. And in case you do not receive my reminder, use the same link that we have been using to access the session tomorrow. Okay, we're going to start the session right now. Kelly, could you go ahead and read for us what we're going to start with today?
Synthesis of alcohols, reactions of Lindblom, burning water, reagents with carbonyl compounds.
Okay, very good. So we are going to start, of course, with continue with the synthesis of alcohols. And in this particular instance, we are going to start with the reactions of Grignard reagents. As you can see here, this molecule here, this is a Grignard reagent. This is also a Grignard reagent. If you recall, when we discussed Grignard reagents last semester, Grignard reagent is essentially you have a bond between carbon and magnesium in the Grignard molecule. But if you want to take a closer look at this carbon here and this magnesium, we know that carbon is more electronegative than magnesium. So therefore, the bond between carbon and magnesium is highly polarized, which means that most of the electron cloud is going to be on this carbon here. Say for example, if we have this, say we have this generic molecule here, which is a Grignard reagent. Imagine that these two electrons here goes all the way to carbon. Okay, goes all the way to carbon. So you therefore think of the Grignard reagent as essentially as this type of molecule in which you have the carbon that is attached to the magnesium is negatively charged. It's a carbon anion, what we call carbon ion. Negatively charged, and therefore the magnesium is positively charged. So we therefore refer to the this part of the molecule here, the carbon ion, has a nucleophile. We all know that, right? So we say this is a nucleophile. Of course, the magnesium, positively charged magnesium is what? It's electrophile, right? Now, what does this mean? When we say this is a nucleophile, what this essentially means is that this nucleophile will be willing to attach itself to any positively charged species. What I'm going to do now, before we go to some of the outcome of the Grignard reagent with different molecules, I would like to give you the mechanism of the Grignard reagent in the reaction with aldehydes, ketone, and ester. If you recall, before we left on Thursday, we showed you a similar reaction with the metal hydride, in which we told you that what you have reacting here is the hydride, right here. So the Grignard reagent also will be doing the same. This hydride here is acting as a nucleophile. So at this point, I really do not have to give you the mechanism of the Grignard, right? You already know it. I should go ahead and do it, eh? It is the same thing. All you are replacing now, just replacing the carbon ion of the Grignard, the hydride with the Grignard anion. That's all you have to do, right? But you want me to do it anyway. Go ahead and do it. Okay, I will. Okay, let us look at the mechanism of the Grignard reagent. With aldehydes, ketones, and esters. Say, for example, let us just start with the generic Grignard. We start with this here. The Grignard reagent, reacting with the simplest aldehyde, which is formaldehyde, step 1, and then step 2, we say we add hydronium ion. What do we get? We get this molecule here. Okay, I tell you what, let me try to differentiate this from, use a different color here so we know what is coming from what. Okay, we're going to represent the atoms from formaldehyde with red. So therefore, what are we going to get here? We are going to get a primary alcohol. In other words, a Grignard reagent will react with formaldehyde, which is this molecule here, to give what? To give what? What kind of alcohol? A primary alcohol. Keep that in mind. If, on the other hand, we have the Grignard, just for the sake of this discussion, let us use the same generic Grignard, and we have step 1, an aldehyde. Keep in mind, formaldehyde is also an aldehyde. That is just the simplest aldehyde. Now we use acetaldehyde, which is this aldehyde here, and then we follow it up with hydronium ion. What we get? We get, oh, forgot to use a different color. Use a different color here. Okay, so in this case we are going to get a secondary alcohol. In other words, a grignard will react with an aldehyde to give a secondary alcohol. So here we have and then we have a secondary alcohol. So a grignard reacts with an aldehyde to give what? A secondary alcohol. But if it reacts with the simplest aldehyde, which is formaldehyde, what does it give you? A primary alcohol. Keep that in mind. Okay. Now take the same grignard. Keep in mind, this is just a generic grignard. It could be any grignard. Step 1, let me take my pen, color my pen. Let us say here, we now take this ketone, this acetone, and then step 2, follow it up with hydronium ion. At this time, we are going to get a tertiary alcohol. A tertiary alcohol. So a grignard will react with a ketone to give what? Tertiary alcohol. Okay, very good. Now, supposing we take an ester. We take an ester using the same grignard, generic grignard. Step 1, let's say this ester here. And then we follow this up with hydronium ion. This time we get also a tertiary alcohol. Also we get a tertiary alcohol. Now look at this very carefully now. This here, we get this tertiary alcohol. The CH3 is still here. This time now, we're going to have 2 of the grignard components in the tertiary alcohol. Even though we get a tertiary alcohol, just as in the case of the ketone, but in the case of the ester, you also get a tertiary alcohol, but this time the two alkyl groups from the tertiary alcohol will come from the Grignard reagent. Yes. Very good. That takes us to the mechanism. That is why we're here. So now let us give you the mechanism of these reactions now. So we've given you the outcome of these reactions. In other words, you know that if you react a Grignard with an ester, you get what? A tertiary alcohol. Now let us see how this happens. Okay, let me erase this. Okay. Let's start with the aldehyde. We told you this is the way you look at the Grignard. Look at the carbon attached to the magnesium as being nucleophilic. Okay, negatively charged. Okay. Of course, the magnesium part is simply just there as a spectator ion. So now you have our aldehyde here. We know that the carbon of the aldehyde is electrophilic because the oxygen, we could write a resonance that would draw this electron to oxygen. Okay? So we could do that, but we don't need to do that at this point. You all know how to do that. So we could simply have the nucleophile come in here, attack that electrophilic carbon, and the pi electron goes to oxygen. At this point, we have this here. You will find that this mechanism is similar to the mechanism of the metal hydride reaction. So now you have this. Hydrogen is here. And now you have, let me change the color, pen. That is coming from the Grignard. Okay, so now you have an oxonium ion or alkoxide. This now, all you now need to do here, now that is the reason why we add the water or the hydronium ion. Add the hydronium ion to that, and that will protonate the negatively charged oxygen. And that is how you get your alcohol. And in this case, you get a secondary alcohol. So now you have this. You have this. You have this. Of course, the hydrogen is coming from the hydronium ion. And then you have this hydrogen is from the original aldehyde, and then you have the component of this molecule from the Grignard. Okay, and that is the mechanism of the reaction of the Grignard with an aldehyde. And it is the same mechanism that you have with formaldehyde, so we don't need to do that. Remember, we told you the simplest aldehyde, it is the same mechanism. Also, it is a similar mechanism for the ketone. Okay, Okay, so if we add a ketone, say this, we are going to react this with a ketone, for example. Okay, so what is going to happen? What is the first thing that happens? Reaction with the ketone. The Grignard anion reacts with, will attack the carbonyl carbon of the ketone, right? Okay, very good. So now you have this come here. Attack that. And here. So you see the similarity in the mechanism. Essentially the same reaction mechanism. So now we have and this material is still here. Now we have the Grignard is here. So at this point, what do? We add the hydronium ion. So that is why when you write the synthetic scheme, you have to write step 1 and step 2, because those are two separate processes. Okay, so therefore you have this case. We now introduce our hydronium ion, and now you obtain your and this hydrogen is from the water, and of course this is the component from the Grignard. Okay, so that's how you get your secondary or rather tertiary alcohol from a ketone. Now let us see how do we obtain the product from the ester. How do we obtain the product from the ester? So again we have our Grignard, which is nucleophilic. Magnesium is here. So now we are going to have ester. Okay? Yes, Emma.
Does it always have to be a CH3, CH2 down to the carbon, to the carbonyl? It could be a...
Oh no, it could be any ester. The reason why I use this is because those are the examples I gave you earlier. So I think they want to be consistent in using the same examples. But this is generic. Okay. Okay, now. So what do you think, what are we going to do first in terms of the reaction mechanism? What will happen now? The nucleophile, right, will attack the, exactly. So it's the same thing that is happening before. So this comes here, attack this, and then of course the pi electron goes to oxygen. So now you form negatively charged. Of course, most of you will wonder what happened to the magnesium. The magnesium will simply just be sitting somewhere around here, next to the negatively charged oxygen. Okay? I know I forgot to add the magnesium all along. Okay, so now you have this. Of course, at this point you still have this here. The methoxy is still here. And now the component from the grignard is here. So far, everything looks so much like the mechanism with aldehyde and ketone, right? Now, this is where the difference is. At this point, you form this intermediate. Ordinarily, this is where you add the hydronium ion. Okay? By the way, some of you will be doing this in the lab. How many of you are doing the organic lab now? Okay. You are going to be doing this reaction, so now you are ahead of everybody. You do not add the hydronium ion before they tell you to add it, because if you do, you will mess up your grignard reagent. Okay, so in this particular instance, what is going to happen, this intermediate is fairly unstable. It will regenerate the carbonyl. Okay, and we know what happens. If it regenerates the carbonyl, something has got to give here. Either this bond will break. If this bond breaks, it goes back to the starting material. On the other hand, if this one should break, if the bond between carbon and oxygen should break, then we get an intermediate product, and that intermediate product happens to be a ketone. Happens to be a ketone. Now the component from the grignard is here, and of course the methoxide is gone. Methoxide is here with the magnesium because it is negatively charged. Okay, so that is how we lose the methoxide at here. That was your question, right? Okay, so that's how we lose the methoxide, this group right here. Now the question is, do we isolate this? No, we don't, because the ketone is very reactive. Remember what happened to the ketone with a grignard? Reaction of ketone with grignard, what does it give us? A tertiary alcohol. So at this point, another molecule of grignard will come and attack this here before you add your hydronium ion. Okay, so another molecule of the grignard will come with, of course, magnesium is here. Attack this just as it will normally attack a ketone. Now the mechanism is similar to the mechanism of a grignard with a ketone. You see that now? Okay? And of course, this will now go here. And by the way, this is the same mechanism I told you guys to work on your own. Remember, I told you with the hydride, with ester, this is the same type of mechanism. Okay, so now you have and then we have here one piece of the grignard reagent, the other piece of the grignard reagent. So at this point, you now add your hydronium ion. You follow that? Okay, that is now why when you react grineal with all of these carbonyl compounds, you got to have allow the reaction to go for a certain number of minutes or so before you add your hydronium ion. So if you add the hydronium ion before, then that would destroy your grineal reagent. Okay, so at this point we have hydronium ion, and that would therefore give us our final product. Okay, this hydrogen is coming from the hydronium ion. Let's see. So you see the two alkyl groups are coming from the grineal reagent. Okay? So now what we've done, we have given you the mechanism of the reaction of grineal reagent with formaldehyde. Yeah, we did not give you for formaldehyde, but you could deduce that from the aldehyde. I will give you for aldehyde, for ketone, and for ester. Okay? Is there any question? Okay, good. Okay, so now you see, let's take a look at this example here. Okay, so this grineal reacts with formaldehyde. You see, it gives you a primary alcohol. This methylene group is coming from here, from the formaldehyde. Okay, the grineal, this grineal reagent, this is called, of course, this is phenyl magnesium bromide. Okay, that is the grineal you guys are going to make when you do your experiment in the organic lab. You are going to be making phenyl magnesium bromide. Okay, and these grineals are very, very reactive. So you really have to be very careful. They react with water, they react with carbon dioxide, they react with just about everything. So you will notice when you do that experiment, you have to take some caution. Okay, so in this case, phenyl magnesium bromide, who is reacting with an aldehyde here, followed by addition of hydronium ion, you form a secondary alcohol. Okay, here we see the grineals. This is ethyl magnesium bromide, the grineal reagent, reacting with cyclohexanone, the ketone, to give the tertiary alcohol. You see this the component coming from the grineal. Here we have a ketone reacting with methyl magnesium bromide. Of course, you see, I'm sorry, this is an ester. This is an ester reacting with methyl magnesium bromide, and you notice what we have here. These two methyl groups are coming from the grineal reagent. Okay, based on the mechanism we just gave you, you should know how that happens. Okay, before we go to the next topic, let us do this problem. Oh, not yet. Okay, this is a small problem here. Now, you notice here, this molecule here, we have so many different ways in which we could make this molecule. I could give you this problem in an exam or a quiz and say, give me the different ways in which you could make this molecule. You see, you have 3 different ways in which all we're doing here is just changing the nature of the carbonyl. Here we're starting with this methyl ketone, with this grineal from the same molecule. So what you do here, when you have this kind of problem, you take an analysis of the product and look at the alkyl group. Okay, based on the alkyl group that you have in the product, you should be able to determine what kind of alkyl group will be present in your ketone or your ester or your aldehyde. In this case, to see how we bury this here to form the same. We have 3 different routes arriving at the same outcome. Okay, very often if you work in the industry or the laboratory, what determines what route you are going to use depends on the cost. Okay, then you begin to look at which is cheaper to make. Okay, so that is why you then begin to look at the cost of the production. Okay, some of you are going to work in the industry. Those are the kind of things you have to think of. You don't just make something; you have to make something that is cost effective. Okay. Okay, now let's see if we can do this problem. Okay, Mike, can you go ahead and read this question for us?
What carbonyl compounds must you start with the Grignard synthesis of the following compound?
Okay. What carbonyl compounds can you start with, would you start with in the synthesis of this compound? Okay, does anybody have an idea what carbonyl compound are we going to use? Okay, we have this carbon. Yes, go ahead. Yes.
Okay. So the ketone with two metals attached to it.
Okay, why do you think we need to start with a ketone? Exactly, excellent, because it is a tertiary alcohol. The moment you see a tertiary alcohol, you know that you're going to have to start with a ketone or an ester. Okay? Okay, so tertiary alcohol. So we could say that this is the ketone part right here. Could that be your ketone part? Okay, in that case it will be this here. Is that Marcellus? Okay. That's your ketone part. Okay, so which will be your Grignard part? Okay, so your Grignard will be this here. CH2. Okay. Okay, now, how will you make the Grignard? Of course, we all know how to do that from last semester, right? To make the Grignard, somebody said no. To make the Grignard, what do you do? Alkyl halide, alkyl bromide. In this case, we could take the alkyl bromide. Okay, if you take that alkyl bromide and simply add Grignard magnesium to it, generally this reaction takes place in the presence of ether as solvent. But if you do not add the ether to it, that's fine. If all you do is simply just give me the magnesium, that will be just fine. Okay, so that's how you make the Grignard. And that's how you guys are going to make the Grignard in the laboratory when you do the experiment. Okay, so that is one answer. What other carbonyl can we use? We say we could use it. What other carbonyl can you use? Okay, let's see here. Which is the carbonyl part? Can we say this part? This part here? Can that be from the carbonyl? Right? Okay. In that case, it will be so that carbonyl will be this. And what will be the Grignard? Methyl magnesium bromide, exactly. So the Grignard will be this here. It will be methyl magnesium bromide. Therefore, to make the Grignard, all we need to do is what? Methyl bromide to magnesium. Okay. Okay, very good. Now let us now we want to now take a look at the reactions of alcohol. So far we have been dealing with the synthesis of alcohols. And keep in mind, for the synthesis of alcohols, we use metal hydride reduction of carbonyl compounds, and also we use the linear reactions of carbonyl compounds, with carbonyl compounds to make the alcohols. So now let us begin to take a look at the reactions of alcohols. Now you will find that for the reactions of alcohol, let me go to a blank page. Most of the reactions of alcohol, if you take a look at an alcohol, generally, the hydroxy group, this group here, it is not a good living group. The hydroxy group never lives. It does not want to live because the carbon-oxygen bond is very strong. Plus, also, the hydroxide is a very, very strong base or nucleophile. So, it is very difficult to have the hydroxide living as a living group. So most of the reactions we are going to encounter will be those in which we are going to try to make the hydroxy group a living group by attaching something else to it. Keep in mind, we told you earlier that we have this non-bonding pair of electrons. If I therefore have this here, hydrogen bromide, to this, what do I get? I get a protonated alcohol in which this pair of electrons will be used to bond to a proton, because the proton is coming without electrons. It has a vacant orbital to share with this pair of electrons. So we have this pair of electrons is still here, and of course this is still here, and therefore this becomes positively charged. The bromide is somewhere here. Now, once you do that, the hydroxy group has now been made into a species that could live as water. Now, water is very stable, so this bond could break very easily, so that will go. So now what happens here depends on the what is attached to this carbon here. If this is a primary carbon, what is going to happen is this bromide could come here, attack this, and this will leave, and this becomes an SN2 reaction. You all remember that? You thought we forgot about that, didn't you? That becomes an SN2 reaction. Keep in mind, SN2 reaction only takes place on what type of carbon? Primary and secondary carbon. Excellent. So therefore, we could get that. If on the other hand, if we have the alcohol is a tertiary alcohol, and you have HBr, hydrogen bromide, or hydrogen chloride, the same thing here. Okay, the first thing that we get is protonation, which will be acid-base reaction. This is acting as a base. Of course, this is an acid, so you get your acid-base reaction. Is that a question or just talking? Okay. So now you have protonation, and of course you have the bromide is here somewhere. Now, because this is a tertiary substrate, what do you think is going to happen? Do you think the bromide is going to come in and attack this carbon here? No, because of steric hindrance, it will not do that. But because it is a tertiary substrate, the water will live as a good living group, and in so doing, what do you have? You now have a tertiary carbocation. You now have a tertiary carbocation. Okay? Now, what happens here? This carbocation could be, because this carbon now, think of it is flat. Okay, the geometry is flat. So the bromide could come from here or from here, from both sides. Unlike the SN2 reaction, where the nucleophile comes from only one side. In the SN2 reaction here, the nucleophile comes from one side. But here, this becomes an SN1 reaction. Keep in mind, in the SN1 reaction, you form an intermediate carbocation. So what this means is, this bromide could come in, could attack this carbon from this side, or it could attack from on this side. Now, what do you think is going to happen? What kind of product do we expect if that happens? I'm going to use a long arrow here. Okay, longest arrow. I should get a Nobel Prize for that arrow, right? For drawing the longest arrow. Okay. So now, what do you think is going to happen? What kind of product are we going to get here? Two products. Now, if this starting material is optically active, then what do you think is going to happen? We are going to lose optical activity, because this carbocation intermediate is achiral, what we call achiral. It's achiral. Whereas, assuming that this was chiral, let us say this is different from this prime, double prime, okay? So this is chiral. So in this case, you are going to lose optical activity because you are forming an achiral intermediate. And here, therefore, what kind of products are you going to form? Two equal amount of enantiomers. And what do we call that? Racemate. So we're going to form a racemate. So you're going to form two . So you're going to have this bromide here, plus the mirror image. Think of the mirror here. Okay, so this is a racemate. When you form a racemate. Unlike here, unlike in this product here, coming from here, in the SN2 reaction, if you start with an optically active material here, the product you get in the SN2 reaction will it be optically active? Yes, in the SN2 reaction. Because all you're doing is inversion of configuration. If you have R, you go to S. If you have S, you go to R in the SN2 reaction. But in the SN1 reaction, if you started with R, by the time you finish, you are going to get a mixture of R and S. And that is why you get a racemate. Okay? I say this because there is some implication to this as a result of the fact that you are going to be losing optical activity. Okay, so that is just now giving you a background. Okay, so reactions of alcohol. The first set of reactions, we could have alcohol reacting with hydrogen chloride or hydrogen bromide to give you alkyl halide. Okay, and in this particular instance, you start with a tertiary alcohol. Of course, you are going to end up with an alkyl halide. In this case, you are going to get a racemate if this is optically active. If this is not optically active, that's irrelevant. Okay? For example, supposing we just have this. Supposing I just give you this here. Okay, so what would be the product? The product would be just this. Because this molecule here, this is not optically active, so you don't really need to worry about that. But if it is optically active, then, and you are told to show the stereochemistry, then you need to be able to indicate that there is a racemate formed. Okay? So here you could use either hydrogen chloride or hydrogen bromide. Okay, of course, this is the mechanism that I just showed you. Okay, another set of reactions, very similar to what we just did, in terms of the hydroxy group, is not a good leaving group, but we could convert the hydroxy group to a good leaving group. It's another set of reactions. If you take, in this case, a primary or secondary alcohol, and you take this molecule here, we call thionyl chloride. Let me take that off. This molecule here, we've used this before, called the thionyl chloride. Thionyl chloride, if you take that, that will convert an alcohol, a primary or secondary alcohol, to an alkyl chloride. Okay, this is also an SN2 reaction. You see what is happening here? The hydroxy group attacks this thionyl chloride to form this intermediate. This now becomes a good leaving group. The chloride comes in from the back, attacks. So if you are starting with a molecule that is our configuration here, by the time you get here, the configuration will be what? Will be S. Because SN2 reaction is goes through the inversion of configuration. Okay? The same thing here, this reagent here, phosphorus tribromide, will similarly convert a primary or secondary alcohol to an alkyl bromide. So if I ask you this, if I say this, what will be the product? What is the product? Bromo cyclohexane. Exactly. If on the other hand, I give you thionyl chloride, then I get chlorocyclohexane. So we could see we could convert alcohol to alkyl halide in so many different ways. Yes, Emma.
So what's like reasoning as why we have to make those HCl, HCl at the same time?
Yeah, those are two reagents. Even though they do, I mean, well, the bromide gives you the HCl give you the, no, I'm sorry, I mean the HCl and the thionyl chloride. Why you have to use Say that again.
Won't HCl do the same thing for comments as needed?
Okay, I got it now. The HCl in terms of converting to the alkyl chloride, yeah, it will do that, but in terms of efficiency, the thionyl chloride is a more efficient reagent. Sometimes when you get to the laboratory, you begin to look at the ease of performing certain reactions. Okay. So yes, HCl with the primary alcohol could do it, but thionyl chloride gives you a better yield. Okay. Another reagent that could also convert an alcohol to what we call a good living group is this molecule here, this reaction here. This particular molecule we call toluene sulfonic chloride. Okay, we call it toluene sulfonyl chloride. Actually, it's a P. Yeah, okay. Toluene sulfonyl chloride. And we generally refer to this as tosylate. This molecule here, this particular molecule is called tosyl chloride. Now, you could take this tosyl chloride react with an alcohol. See, all we've done here is to displace the chloride. Now we form what we call the tosylate. Okay, this is the toluene sulfonic chloride, which is this, and this is now the tosylate. Once we form the product with the alcohol. I know a specific example here. Take this here, this alcohol here. You notice the stereochemistry here is R. The stereochemistry here remains R, which is to tell us that the stereochemistry of this carbon is not involved in this reaction. Keep in mind, all that is involved in this reaction is the breakage of the, in this particular instance, the breakage of the oxygen-hydrogen bond. At no time do you break this bond. So that is why the stereochemistry remains the same. Okay? But as you're going to find out as we go along during the course of this semester, this here is a very, very good living group. This group here, okay, it behaves just as any other living group like the chloride, the bromide. So in many reactions that we want to do, the substitution reaction, what we do, we convert the alcohol into a tosylate, and then we could then do an SN2 reaction on this molecule, because this is a very good living group. Okay? Okay, you also see here, this is the way the molecule is written. You don't have to write it this way. You could simply just have P-tosyl chloride, which is P stands for para, because the methyl group is in the para position. Okay. So you could use the tosyl chloride reacting with an alcohol to form the tosylate. Okay, this is just some other examples. Okay, here what do we have here? Phosphorus tribromide reacting with this alcohol here. We have the stereochemistry, R. We have an inverted configuration because this reaction proceeds with inverted configuration. If you go back to, let me show you again. Go back to here. Remember, the first thing that happens, hydroxy group attach this phosphorus, replacing the bromide, which is right here, to form this intermediate. The bromide now comes attached on the back in an SN2 reaction. The same thing happens here. Okay, of course here we show you a reaction in which we have the tosyl chloride reacting with the alcohol. Here there is retention of configuration, because that reaction does not involve the breakage of the oxygen carbon bond. Okay. Now let us, we've seen this before, we don't need to spend too much time on this. Dehydration of alcohol. Remember when we did alkenes, we actually used this slide before. In the presence of dilute acid, you react an alcohol. In the presence of dilute acid, you form a carbon-carbon double bond. And if you remember, we told you about the this rule. Okay, this is rule that we gave you earlier. Is this rule tells you that anytime you form an alkene, a carbon-carbon double bond, you are going to form the most stable alkene. In this case, the most stable alkene will be the most substituted alkene as the major product. Okay? So when you do this here, we have two choices. The double bond could be here, or the double bond could be here. But here, the major product is this here, in which you form the most substituted alkene. Okay? The same thing here. Reacting this alcohol with this, of course, you form these two products here, this and this. And I'll tell you now, this is the major product. So this is the most substituted. Yes. Okay. Now, okay. So now, the last reaction in terms of dehydration of alcohols, phosphorus oxychloride. Emma, you remember this reagent, the last that I said that, yeah, okay. Yeah, and I said this would be the reagent for the bromide, and I came back and said that was not, yeah, okay, this I was thinking about this one here. What happens if you take an alcohol and you want a very mild way of dehydrating the alcohol? This is a very good reagent for that, phosphorus oxychloride. Okay, of course, you still have to follow the same Z rule in terms of forming the more stable product, okay, which is what this is here. So this is a good reagent for dehydration of alcohols. And I think we are almost, okay. What time do we have? Oh, we have plenty of time. Always plenty of time. Okay. This here, we continue the reactions of alcohols. Alcohols could be converted. You could use alcohol to make esters. In this case, if we take an alcohol, you could react an alcohol with a carboxylic acid to form an ester. That is how we form ester, in the presence of some acid catalyst. This here, the ACL is acting as a catalyst. When we get to the chemistry of esters, we will show you the mechanism for this reaction. You could, however, because this particular reaction, you have to heat it up for a while before it goes. I think some of you will be doing this also in the lab, in which you are going to take benzoic acid. Have you done that already? Those of you doing lab, have you done the esterification of benzoic acid? Okay, you are going to do that. You take benzoic acid, you react with methanol to get methyl benzoate, and this is called Fischer esterification. Okay? Simply just taking an alcohol in the presence of carboxylic acid gives you an ester. On the other hand, if you want a mild way of doing it, you could react the carboxylic acid with thionyl chloride to give you the acid chloride. Notice what have we done here. What does thionyl chloride do? Replaces the hydroxy group with the chlorine atom to form what we call the acid chloride. And this acid chloride will very easily react with methanol or any alcohol to give you the ester. So there are two ways in which you can form ester, either directly by reaction with carboxylic acid with alcohol in the presence of acid catalyst, or conversion of the carboxylic acid to acid chloride and then subsequently reacting the acid chloride with an alcohol to form the ester. Yes. Yes, this here, going from here to here, I mean, if you just add both of them together, it's almost instantaneously. Whereas this here takes a while. You have to actually apply heat. Okay, so that is sometimes you may want to go take the extra step to go here. From here to here is fairly easy to do, even though this is a very nasty reagent. You don't really want to work with it sometimes. And then from here to here is also easy. But here, you almost have to heat this up for about 1 hour. So it all depends on the experimental condition. But you don't need to worry about that. Just if I ask you to make the ester, just make it at this point. Okay. Okay, so now finally we now almost the last two reactions for this chapter and then the end of the chapter. Now we want to discuss oxidation of alcohols. Oxidation of alcohols. Okay. I want to give you something that is not in your book, so you may want to pay attention to this. If you have this, that molecule, of course, you all know that molecule, right? What is the name of that molecule? Methane. Okay? You look at the oxidation state of this carbon. We say that carbon has an oxidation state of -4. For each carbon atom and for each hydrogen atom that is attached to carbon, you give it an oxidation state of -1. So because this is attached to 4, therefore that carbon has an oxidation state of -4. So if we then go to the next molecule, supposing we replace the hydrogen with an oxygen, we replace only one of the hydrogens. So now we have this. Okay, anytime the carbon is attached to oxygen atom or any atom that is more electronegative than carbon, then the oxidation state is +1. Okay, so in this case, you have -1, -1, -1, that's -3. Then you have oxygen, that's +1. So what will be the oxidation state of this carbon? What is it? -3 + 1, -2. Okay? So we go to the next one. Supposing we have this, we now replace 2 of the hydrogens. We form an aldehyde. Okay? What will be the oxidation state of this carbon? For each double bond, for each bond you have here, this is +1, this is another +1. Okay? For each bond is a +1 attached to oxygen. So in this case of carbon-oxygen double bond, that is +2. Okay, so you have +2 -1 -1, what is that? 0. So the oxidation state of that carbon is 0. Now, if we now go to replace 3 of them, we now form a carboxylic acid. What is the oxidation state of this carbon? Oxidation state of that carbon. What is it? 2. Okay, this is 2. This is +2, +1, and -1. Okay, that is +2. Okay, and finally, let us now go to the most oxidized carbon atom. Let us now say we go to carbon dioxide. what will be the oxidation state of carbon dioxide? +4. Okay, so you can see here, oxidation, when based on what you did in general chemistry, oxidation is what? Is the increase in oxidation state of a given atom, right? And that is what we are going to be doing here. Or the way you may want to look at it, since we are going to be dealing mostly with oxygen, oxidation is the increase of the oxygen content of a carbon atom. Okay? Whereas we could define the reduction as the decrease in the oxidation state. So going from carbon dioxide to methane will be reduction. Or the other way we can look at it is the increase in the hydrogen content of a carbon atom. That is reduction. Okay? So that is why when we did the metal hydride reaction, we said those were reduction reactions. Okay, so let us now see. What reagent do we need to do oxidation? Not too many. If you take a primary alcohol, you could use this reagent here, chromic anhydride, in the presence of acid. Actually, this reagent here, what happens, it generates chromic acid in situ. In other words, it generates the chromic acid in the reaction pot, chromic. Okay? You could be giving chromic acid just as this, or chromium trioxide in the presence of acid. What it does, a primary alcohol will be converted to what? To a carboxylic acid. Okay, and that is the reagent that does that. Now, if on the other hand, you want to convert a primary alcohol only to an aldehyde, you use this reagent here. This reagent here, we call this pyridinium fluorochromate. So we have the acronym PCC. So this is PCC. So you don't need to write this when you give this reaction for me or for anybody. You don't need to write this molecule here. Just say PCC. What this reagent does is to convert an alcohol, a primary alcohol this time, to an aldehyde. Because if you use chromic acid or chromium trioxide, what you get is carboxylic acid. So there is a distinction there. And also there is another reagent that you could use to convert an alcohol to an aldehyde, and that reagent is this here. It's iodine. Attached to acetate. Okay, another acetate, because the acetate OAC stands for the acetate, another acetate. Of course, you don't need to write that big molecule. We simply refer to this molecule as des Martin per iodine. So for you, all you have to do is just write des Martin. Okay, we know what that means, and that will convert a primary alcohol to an aldehyde. So it will do the same thing that PCC will do, just that it is a milder reagent than PCC, but more expensive. Yes. To add, yes. But yes, okay. They will convert the primary alcohol to an aldehyde. But PCC will react with something else. Let me show you the next slide. Very good. Okay. So I thought I had that. Okay. Anyway. Let me go through my blank. PCC could also convert a secondary alcohol to a ketone. PCC will convert a secondary alcohol to a ketone. So also is chromium trioxide will also convert a secondary alcohol to a ketone. Okay? Now, but the utility of PCC is that it will only take, convert a primary alcohol to an aldehyde. Okay, not to carboxylic acid. Okay. You follow that? Okay. PCC will convert a primary alcohol to aldehyde. It could also convert a secondary alcohol to a ketone. Okay. Okay, before we...
Just only primary?
Yes, only primary. Okay, let's do a couple of questions, the problems before we leave. What time do we have? For 3 minutes. Okay, do you want to try this problem here? Or you could do that on your own? You want to do it now? Okay, we do it online? Okay, very good. Okay, I do have a bunch of problems for you. Just in case when you watch this video, okay, that's the solution to that problem. Okay, so you watch the video and you see it. Then the next problem is that problem here. And the solution is also right there. Okay, and the next one is this is another solution to the same problem. Okay, this one here, solution to that. So I urge you to definitely take advantage of this and watch the video, and of course you could always pause the video and record this. So anyway, this is the end of chapter 17. There's one more reaction, but we are not going to do that now. We are going to start chapter 18 on Thursday, and there will be a short quiz on Thursday on chapter 17.